So hello and welcome class. So this is Fluid Mechanics and I'm Engineer Ranjan Argami. So today we will have additional problems on buoyancy. So for our learning objectives for today, at the end of the session, of course, you'll be able to interpret the conditions in the problem. Then illustrate the free body diagrams. And then apply Archimedes' principle of buoyancy on problems. So let us have additional problems. So we have here a 5 cm by 12 cm by 6 meter long wooden plank is required to stand 15 cm seen above the water surface. This is attained by attaching 1 cm thick plate on the wider sides only near the submerged bottom. How long should the plate be? So in here, we are going to illustrate our free body diagram. Okay, so we have also the properties of the water, wood, and steel in terms of the density. So the raw for water is 1002 kg per cubic meter. And for wood, we have 502 kg per cubic meter. And for the steel, we have 7,870 kg per cubic meter. So remember that the steel here will serve as an anchor for this wooden plank to stand wherein 15 cm is seen above the water surface. So to illustrate that, let us have the water surface here, and then the water will be in terms of the density, 1002 kg per cubic meter. So we let this wooden plank to stand upright position, wherein 15 cm is seen. That would be equivalent to 0.15 meter. And if the total length of this wooden plank is 6 meter, of course, 6 minus 0.15, that is 5.85 meter. So 5.85 here is noted to be the submerged length. So we also need to indicate the width of the plank for the computation of volume later. And the side view will have the thickness to be equal to 0.05 meter thick. And then this blue here, rectangular plates, a steel material. Of course, again, I would like to reiterate that this will serve as its anchor. Okay. So this steel is 1 cm thick, or that is 0.01 meter in equivalent. So this is the projection on the section. And our task is to determine the length, or the length of the plate. So first, we need to note that there will be a weight for our wooden plank. There must be also corresponding weights for the steel plates. And the submerged portion will have its buoyant force. For the steel, we have the whole volume to be submerged, and that would have a corresponding buoyant force for the steel, say denoted by FB of steel. And the portion 5.85 length for wooden plank has also its corresponding buoyant force. So our solution So obviously, we'll take off from the equilibrium equation along the vertical. Summation forces vertical is equal to 0. We have the downward forces will just be equal to the upward forces. So we have the weight of wood and 2 weight of steel. So those are the downward forces will be equal to the upward forces. So all of the upward forces are the uplift forces caused by the buoyant force. So we have the buoyant force for the wooden plank plus 2 buoyant forces for the steel plates. So we expand our equation for the weight of wood. So the weight of wood is gamma times volume plus 2 times gamma volume of the steel is equal to, we use now the Archimedes principle. So the formula is similar, gamma times volume, but this time gamma will be the fluid itself. And the volume involved is the volume submerged for the wood. For the steel, we have 2 of the buoyant forces. We have gamma of the fluid times the volume of the steel submerged. We expand gamma in terms of density because in the problem, the density property is given. So therefore, we need to expand our equation in terms of rho or density. So recall that gamma is equal to rho times specific rho times acceleration due to gravity, or rho times g of the wood. Okay. Likewise, for the steel, we have rho g for the steel. And for the fluid, of course, that is rho g for the fluid. And rho g for the fluid. Okay, so notice that g is common to both left and right hand equation. Hence, is common to all terms in the equation. So therefore, we can just cancel that. Now, we can directly substitute 502 for the wood. And the volume for the wood is length times width times height. So the thickness is 0.05. The width is 0.12. And the total length is 6 meters. So take note that in the weight, we are considering the whole volume. So we add the steel, the weight for the steel, we have 2 of them, and the rho is 7,870 kilogram per cubic meter. So the volume of steel is the thickness 0.01 times the width 0.12 times the length, which is unknown, L. Now this is equal to the buoyant forces on the right hand side. So in here, we use the density of water or the fluid involved, 1002. So the volume for water or for the wood submerged is 0.05 times the width 0.12. So this time, we are only concerned with the submerged portion, which is 5.85. So we do the same for the buoyant force of the steel. So we add that one. There are 2 of them. So the involved fluid is water, 1002. So the thickness is 0.01. The width of the plate is 0.12 and the length of the plate is yet to be determined. So notice that in our equation we have only single unknown L. We simplify and calculate the first term, the second term, and we have the variable L on the second term. That will be equal to the first term of the right hand side of the equation, and of course 2.4 will have its pair L. So by manipulation, we can compute L to be equal to 1.04 meters. So this is the needed length for this wooden plank to be in upright position, having 15 centimeter length exposed. Okay, so this is for that problem. So moving on to the next problem. In here, we have a block of wood with specific gravity of 0.65. So this block of wood is 20 millimeter thick, which floats in seawater of specific gravity of 1.03. Find the area of a block of wood which will just support a man weighing 80 kg when the top surface is just at the water surface. So again, we need to interpret and illustrate it correctly for our correct solution. Of course, if you do not have an erroneous assumption in your illustration, you will have an erroneous answer. So as a solution, of course, first things first, we need to illustrate the water surface and the block of wood. So the block of wood is totally submerged. So note that according to the problem, the submerged portion or the top will just touch the water surface. So in here, we will have a man that weighs 80 kg. So that will be part of your free body diagram. And of course, the property of the specific gravity of seawater, which is 1.03. We also have the weight of our wooden block. So we have the weight of wood and the corresponding buoyant force of wood. So in here, we'll just have to perform summation forces. Vertical is equal to 0 since we have collinear forces. We have the downward forces will be equal to the upward forces. So the downward forces, we have the weight of man plus the weight of wood. So this will just simply be equal to the buoyant force of wood. So there will be no other forces here. You can now substitute. So in here we have the weight of man. Of course, the weight will be in terms of a force unit. So we need to multiply that by acceleration due to gravity to make it in Newton. So we add the weight of wood. So the weight of wood is gamma times volume of wood. So in here, again, we apply the Archimedes principle that buoyant force is equal to gamma of the fluid times the volume submerged. So in here, we need the wooden volume. So 80 times G. We substitute, of course, in here, we need to express gamma in terms of rho g. Likewise, for rho g of the fluid, so that we can cancel the common term on both left and right side of the equation g. So that will be cancelled. So what is left is 80 times the rho of water. By the way, rho of wood can be also written as rho of water times specific gravity of the material. So volume here can be written as area times the thickness of wood. So for water, the fluid involved is water, of course, times the specific gravity of the seawater. By the way, rho of water or raw water is actually the standard substance. And again, the submerged volume will be in terms of the area of wood times its thickness. So 80 plus, just substitute the rho of water, which is 1000 kilogram per cubic meter. The specific gravity of wood is given 0.65. The area of wood is unknown. And the thickness of wood is given to be equal to 20 millimeter, or that will be equal to 0.02 meters. So we substitute the rho for water in the right hand side of the equation. The specific gravity of seawater is 1.03. The area of wood is unknown. Likewise, we have same thickness of the submerged portion, 0.02. So in here, we have a common unknown, area of wood. By manipulation, we can compute area of wood to be equal to 10.53 square meters. So this is the answer to this problem. Moving on to the next problem. A floating cylinder 10 centimeter in diameter and weighing 982 grams is placed in a cylindrical container 25 centimeter in a diameter that is partially full of water. What is the increase in the depth of water in the container due to placing the float in it? So, as usual, we are going to have a correct assumption in our illustration. So, as a solution, let us first illustrate our cylinder container that is 25 centimeter in diameter. So, this is partially filled with water. So, first, I have to illustrate that this is my original depth. And we have a floating cylinder that is 10 centimeter in diameter. So this floating cylinder will be placed in the cylindrical container. Okay, so let us place that in here. So if we're gonna place that float, of course, there will be an additional, or the depth will increase because of the volume that was inserted. In short, the space that was occupied by your floating cylinder will have its corresponding depth increase. Now, this will now our final depth. We're gonna label certain increase in depth, that is x, which is actually the unknown in the problem. So let us denote that x is the depth increase. So of course, we need also to label this inserted depth here, say that is y. So this is the depth inserted. Why do we need to indicate the depth inserted? Because in Archimedes' principle, we are concerned with the total submerged volume. Hence, we are concerned with the total submerged height. And the submerged height here will be x plus y. So notice that the depth inserted here, the space occupied by this depth inserted, will be the corresponding space of the depth increase. Okay? Again, the depth inserted here is equivalent to the depth increase. Okay. So this is the volume inserted. That will be equal to the volume increase. So that's the logic. So the volume inserted here is the volume of the float with the height y. So that is a cylindrical volume, pi over 4 times diameter squared, or 0.1 squared, times the height of the inserted volume, that is y, and this will be equal to the volume increase. Notice that we have a difference on the larger cylinder and the cylinder occupied by the float. So the larger cylinder has a diameter of 0.25 or 25 centimeter. That is according to the problem. That will be squared and will less 0.1 squared, or the diameter of the float. So this is just a difference in area of the larger circle, the smaller circle. So we multiply that by the common height x. So this is actually the volume increase. Notice that pi over 4 is common, so we can simply cancel that one. We can simplify the left portion of the equation as well as the right hand side of the equation. So in here we will have a relationship between y and x. So here I will express y in terms of x, which is equal to 5.25 of x. So let this be equation 1. Of course, we need to obtain another equation. This time, I'm going to utilize the Archimedes principle. So we have first the weight of that float, that is 0.982 kilograms, or 982 grams equal to 0.982 kilograms. So there will be also corresponding buoyant force for the submerged portion of this float, that is denoted by Fb. So by summation, forces vertical is equal to 0. The buoyant force is equal to 0.982 times g. So simply, the weight is equal to the buoyant force, and the weight is 0.982. 0.982 here is mass, so we need to multiply that by acceleration due to gravity to make it a weight. Okay, and then for the buoyant force, by Archimedes principle, that is gamma of the fluid times the submerged volume. So we retain the right hand side of the equation, 0.982 times g. So in here, gamma is again expanded to rho g. rho of the fluid times acceleration due to gravity. And then we multiply the volume. The submerged volume will be considering the total height of the submerged, or the total submerged height, which is x plus y. Again, this is a cylindrical volume of the float, pi over 4 times 0.1 squared times x plus y. So that will be equal to 0.982 g. So g again is common to our equation, so that will be cancelled. So we substitute the rho for the fluid, 1000, which is water, 1000 kilogram per cubic meter. So we multiply the volume. So we retain this one, and we'll come up with an equation in terms of x plus y that will be equal to 0.125. So let this be our equation 2. We have two equations with two unknowns, that is x and y. So we simply substitute equation 1 to equation 2. So x plus y is 5.25x, is equal to 0.125. So this time, we can now compute for the value of x, which is 0.02 meters. So that will be equivalent to 2 centimeter increase in depth, which is the unknown in the problem. So that's it for this problem. Moving on to the next problem. In here, we have a 2 inches by 2 inches, this is the cross section, by 10 feet length spar has 7-pound steel weight attached as shown in the figure. The boy has lodged against a rock that is 7 feet deep. Compute the angle theta at which the boy will lean, assuming the rock exerts no moment on the boy. Specific gravity of wood is equal to 0.62. So basically, our task here is to get the angle theta, or the leaning angle with this setup. So notice here that our total length of the spar is 10 feet. So that is actually parallel dimension to your spar. If we could only determine this length, then we can just simply determine our theta by using cosine function. So by the free body diagram, we have the center of gravity, wherein there will be a weight of the spar, and the center of gravity of the submerged portion, BO. We have the buoyant force, and that is noted to be L over 2, if that would be L. If our length submerged is L, therefore, that is L over 2 from BO. So at point A, we have the weight of the steel attached to the spar, that is 7 pounds. So this time, summation forces vertical would no longer be equal to 0. Why? Because as you can see in the free body diagram, there are 3 forces involved. So we compute for the weight and the buoyant force separately. We do not equate weight to the buoyant force because there will be 7 pounds along the vertical forces, so we cannot equate the weight to that of the buoyant force. So weight here rather will be equal to gamma volume, and gamma will be expanded to the gamma of the standard substance times the specific gravity of the material times its volume. So gamma of water is 62.4 PCF, or pounds per cubic feet. The given specific gravity for the spar is 0.62, and the volume is 2 by 2 by 10. So 2 by 2 is in terms of inches, so we need to convert that to feet by dividing conversion factor of 12 squared. Why 12 squared? Because 1 foot is equal to 12 inches. And we have a square dimension here because 2 and 2 will be multiplied. So you need to square your 12 conversion factor. So we multiply that by the length to make it volume. The length is 10. So therefore, W can be obtained to be equal to 10.75 pounds. For the buoyant force, using Archimedes' principle, we have the gamma of fluid, gamma of water, times the submerged volume. So this is equal to 62.4. Of course, gamma of water, or specific gravity of water, is 1. The volume, we have the same cross section, but this time we multiply it by the length, because the length submerged is unknown. So we get the value of the buoyant force in terms of the length, 1.73 times L. So we need another equation to come up with the unknown L. So this time I'm gonna use equilibrium equation on the moments. So summation moments at A. So YA, because to eliminate the moment arm of one of the force, that is 7 pounds. So we take moments clockwise positive. So W will have a positive rotation, that is a clockwise rotation, multiplied by the moment arm, so the distance from G up to point A. Same, I'm going to denote that by X. We utilize the triangle formed out of it. So this is X with the corresponding angle, and the length of the triangle will be half of 10. Why half of 10? Because the weight, the reference of the weight is from the center of gravity, and the center of gravity is located mid-dimension of the total length, which is 10. And that mid-dimension happens to be your hypotenuse of your right triangle. So with this, we can simply use the sine function to relate x, 5, and theta. Sine of theta, opposite of theta, is x, divided by the hypotenuse, 5. So x by cross multiplication is 5 sine of theta. Place that into the moment arm of W. So we less the rotation effect of the buoyant force, which is counterclockwise. So So the buoyant force will also have its corresponding moment arm. Say, I'm going to denote that by Y. We utilize the right triangle formed out of it. We have the dimension. This time, the hypotenuse is half of the dimension of L. Similar to that of G a while ago, the submerged portion L, the center of the buoyancy, will be the mid-length of L. So therefore, that is L over 2, which happens to be the hypotenuse of your right triangle. Similarly, by sine function, we can get that y is equal to L over 2 times sine of theta. So we place that as the moment arm for our buoyant force. It is L over 2 times sine of theta. And that equates to 0. In here, we start to transpose the buoyant force to the right side of the equation. Notice that sine theta will just be cancelled on both sides of the equation. We substitute the value of W, which is 10.75 times 5. That will be equal to, we also substitute the value of the obtained buoyant force in terms of L, 1.73 L, times the remaining term on the right portion of the equation. So we multiply 10.75 by 5. 2 came from the cross multiplication of L over 2 from the right portion. So in here, your L will be doubled. Your L will be squared. So therefore, L will be equal to 7.88 by manipulating that equation. So knowing L, we utilize this right triangle here, okay, by relating 7 to the L and the angle theta. That could be done by writing cosine theta is equal to 7 all over L. L, 7.88, we substitute that into the function so that we can determine the angle, 27.33 degrees. So this will be the answer to this problem. And that's it for this session. Have a good day, class, and thank you.